Today we will speak about duality. Duality, given a linear programming problem. Out of this we will make a dual problem. dual يعني مناظرة أو مرتبطة فيها. So given a problem, we will make a dual problem. These two problems, the original one, which we will call primal problem, الأصلية المعنى نسميها primal, and the new one would be called a dual problem. They are related. The solution, the optimal solution of this and this are related somehow. And we will learn such a relation in the next two sections, okay? So today we will only introduce what is a dual problem is and see some properties, theorems relating the primal and the dual problem. Okay, let us make that clear by starting with an example that we have seen in section 1.1. Okay, so in that example, remember, it was about making two kind of foods where each kind must provide some value of fat and carbs and protein, and the cost of each food was for food A 20 cents and for food B 25 cents. Okay, so we have already seen this problem, okay? Now in blue here, this table give us the problem in blue. So this is our original problem. Minimize the cost, okay, subject to. So if we have food A to be x1, food B to be x2, then 2x1 plus 3x2 must be greater than or equal to 12, because that example requires the two kind of foods together to provide at least 18 units of fat and at least 12 units of carbs and 24 units of protein. So we already have seen this linear programming problem coming out, okay? Okay. So what is new now? Out of this problem, we will make a new one, which we call a dual problem. So this, we will call it later a primal problem. The original problem, that's what we mean. The original problem, primal problem. Out of this, we will make what we call a dual problem. So we will make another linear programming problem out of the first one. How? Okay, the way it goes, the following. You see, instead of using 2 times x1 plus 3 times x2 greater than or equal 18, so we go the Kolman way. You see that? 1x1 plus 3x2 greater than or equal 12, 4x1 plus 3x2 greater than or equal 24. Instead of going that way, we will go a horizontal way. What I mean? We will do the following. Okay, before we go, I will call now the three kinds of resources. These are called resources. So I will give a variable for the fat, which is W1. And the variable here means the number of units. It is here said the manufacturer set the price of 1 unit of each of the following, of each of these. So the idea here is when the manufacturer makes the food, he wants to sell them. So he will put price. So he will say the price of 1 unit of fat is W1, price of 1 unit of carbs W2, and W3 is the price of unit of protein. Okay, now we will go horizontal. 2 times W1 plus 1 times W2 plus 4 times W3. So the prices, we want it not to exceed 20 cents. Okay? Because the buyer will buy food A at 20 cents. So we will not make it more than that. And therefore we obtain this equation. So this is the 2, 1, 4. So we have 2, and in here say 1, and in here say 4. So you get the idea? So I will write here 1. And this is less than or equal 20. And this 20 is here. Is less than or equal. Same thing now, we go again for 3W1, 3W2, 3W3, add them together, and then we want this to be less than the cost allowed for the buyer for food B. So we have 333 less than or equal 24. So notice here the less than or equal. Okay, and now for sure we want the variables to be non-negative. Okay, now see what happened. Let's talk about the function to maximize. We want to maximize what? The manufacturer wants to maximize the profit. Maximize the price at least, let's say. And the nutritionists want at least 18 units of fat, okay? So the manufacturer will say, okay, we will have 18 units of the price of 1 unit of fat. And the nutrition wants 12 units at least of carbs. Then we'll say, okay, so each unit of carbs will be multiplied by 12. And same thing here, each unit of protein will be multiplied by 24. And the manufacturer who sells the food, not the nutritionist, the manufacturer, want to maximize that. So the idea here is to maximize this, the function, the new function. So let me highlight it this way. So where this 18 and 12, we have seen where this 18, 12, and 24 came from. Actually, they came from the constraints, the right vector of the constraints. Too much highlighting, let it be visible, huh? This is 14, okay. Okay, good. Now notice what is happening. If we go back to the original problem, leave the table now. Then we will have, this is the vector we used to call, this is vector B, right? This is vector B. So what happened for B, it is now here. The components of B, right? Okay, now again, what happens to these 2, 4, 1? They are here. So the coefficients of x1, we took them to make the first constraint. And the coefficient of x2 here, from all the constraints, we take them to make the second constraint. So again, the coefficient of the first variable are used to make, let me say it again. The coefficient of the first variable in the primal problem, all the coefficients of the first variable in all the constraints are used to make the first constraint in the dual problem. So the coefficients of the first constraint in the primal problem are used to make the first constraint in the dual. Again, the coefficient of the second constraint, second variable, the coefficient of the second variable in all constraints in the primal problem are used to make the second constraint. Then I will say in general, the coefficients of the ith variable in all the constraints in the primal problem are used to make the ith constraint in the dual problem. This is the way we go. Okay, and now the vector of resources B in the primal is used as a cost vector in the dual, and also the cost vector in the dual, which is these ones here. Let me go this way. 20 and 25. This is the cost vector are used as the resources vector. So this is the way. So we will write all of this. You know, this Z is equals, let me write here, Z equals C transpose times X, right? Okay. Now this C transpose is here. Now this is C. So this is the idea. If I want to summarize what is happening here, the cost vector of the primary problem is now the resource vector of the dual, and the resource vector of the primary problem is the cost vector of the dual. The coefficient of the ith variable are the coefficient of the ith constraint. Let us take all this information now and define what is the dual problem in general. So assume we have a linear programming problem given by this table, and you see here that this table gives us the constraints. So using the first column, we obtain the first constraint of the primal problem. Using the second column, you are familiar with these things, we get the second constraint. Now using the ith column, wherever I is, it can be 1, it can be 2, it can be anything, we get the ith constraints, which we have here in general. Now the coefficient of the first constraint, the coefficient of the first variable in all constraints in the primal problem is the first column. The coefficient of the second variable in the primal problem in all constraints is the second column. So the coefficient of the ith variable in the primal problem in all constraints, the coefficient of the ith variable in all constraints in the primal problem is the ith column we see here. So these columns will be used to give the constraints of the dual problem. So we will use this column here, and we will write, before we start actually, we will say, okay, we will give this W1, the first resource, second resource W2, Wi, and we keep going. Now, using the first column in here, we will have the first constraint of the primal problem, dual problem, sorry. So we'll have A11 times W1 plus A12 times W2, and we continue A13 times W3, and we keep going till we get, we assume we have, for example, we end at WS, maybe, okay. So till we reach A1S, WS, this will be less than or equal what? Less than or equal, somebody tells me in general. Can somebody tell me comparing to less than or equal C1? Here the resources will be the cost The resources vector will be the cost, right? So less than or equal C1, correct, in S. Okay, now again we use that. We will have A21W1 plus A22W2 plus A23W3. Keep going all the way. A2SWS less than or equal C2. Now we keep going in general, so we will have AI1W1 plus AI2W2 plus, and we keep going all the way till we get what? AISWS less than or equal CS. Or we write it this way, it is AIJ let me, okay, 1 1 1 2 1 3 2 1 2 2 2 3. Okay, so J from 1 to S, WJ less than or equal CJ. So in general, this is the constraints, and J between 1 all the way to S, the number of the resources. These are the constraints of the dual problem. The constraints of the dual problem. Okay, now what about the cost of the objective function? So we have here maximize, then the objective function of this dual problem is minimize. So we go the opposite. If it is here maximize, we go here minimize. But who tells me what is now z prime here? What I use? So the variables here are these ones. But my question now, what I use as coefficients? I already said the cost function above in the primal will be the resources. The cost vector will be the resources vector. The cost vector in the primal will be the resources vector in the dual. And the resources vector in the primal will be the cost vector in the dual. So what do I fill in here? So tell me what I fill in here. Okay, so I fill in here as Ina said, B1, B2, all the way to Bn. So these are the resources vector. The resources vector in the original problem comes out to be the dual vector, the cost vector in the dual problem. Okay, you are saying we have in the first quote we have a mistake. One of the indices 1 1 1 2 1 3 1 J 1 1 1 2 1 3. So what mistake do I have? No and Siham, you observe something? 2 2 1 2 2 2 3 2S. Second coefficient is A22. This is A22, maybe it's not very clear. A22. This part is the A. It is okay. Is now okay. Here A21, A21, A22, A23, and so on. Is that fine? Confirm, please. A11, A12, A13. In the first, second coefficient, in the first equality, A12. Right? Do you mean this? A12, right? It's A12. Okay, they are okay. Okay, good. Now, let's do it in general now. How we convert a primal to how we make a dual out of primal. The idea is very easy and direct, but I wanted at the beginning to introduce it in a detailed way. But if you go here, this is how things go. So if we have the primal problem, our original problem, see what's happening. This is the cost vector, C1x1 plus C2x2 and so on, which means, to make it clear here, we mean that Z equals C1, C2, all the way till we reach Cn, times x1, x2 till we reach xn. Okay? So when we multiply, we get that. And subject to the constraints as we have seen them, x is n times 1 vector, so A is m times n matrix as we have seen before, and this is the resources vector, B. Now the dual, as we said, the cost vector in the dual is the resources vector, which I mean what we do actually, we will replace, to obtain the dual, what we do to obtain the dual, we will replace the rules of this. This is because the cost vector in the dual is the resources vector in the primal, and the resources vector in the dual is the cost vector in the primal. So we will interchange the rules of C and B with the transposition. Okay? And the rule of A will be replaced by its transpose. It is that easy. And W's are the new variables. Okay? And W is m times 1 Kolman vector. So if I go back here, I called it S to make that consistent with to make the above consistent with things below. So we will call this M. So I will use M here, just to use the same letter. Okay. Okay. And in here, and in here, M. Okay. So the dual problem is that easy. Yes, very easy, huh? And for sure, working an example will make things more clear. We have worked an example above there, but let us here do it again for another example, and so quick. Okay, so assuming okay, this is the original primal problem in here, this is the primal problem, and this is the dual problem. So what we do, we have taken the vector here, the cost vector, and we made it here to be the resources vector, and we have taken the resources vector from the primal, and we made out of it the cost vector, and we have taken the matrix A in here and replaced it with its transpose. That easy. We have two variables above there and three variables above down there. Okay, see the idea ايش هي؟ عدد الفاريبلز اللي في الدول يساوي ايش؟ مين يجاوبني؟ كيف انا بحدد عدد الفاريبلز في الدول؟ بتعلق بايش؟ ال W1 2 3 اللي هم كانوا فوق W1 2 3 لعند WS رجعنا سميناهم WM. كيف بحدد عدد الفاريبلز الجداد هذول؟ مين بيقول لي؟ بناء على ايش؟ كل واحد من هذول الكولومونز every column gave me every column gave me a constraint, and every constraint, what is the number of columns? Tell me. What is the number of bees? No, both of you are right, but that means number of what? What are these? Number of what? Number of constraints. نعم. Thank you, Siha. So the number of W's, the new variable in the dual problem, is the number of constraints. Good? Okay. In the primal problem. So the number of constraints in the primal problem. Okay. And the opposite, the number of constraints in the dual problem is the same as the number of variables in the primal original problem. صح؟ هذول dual معناه عكس هيك وهيك. هذا cost vector هذا resources. جميل؟ لكن الكوست فيكتور هنا بيكون resources هناك، والكوست فيكتور هناك بيكون resources هناك. number of variables هناك هو number of constraints هناك، و number of variables هنا هو number of constraints هناك. تمام؟ اوكي. اوكي جميل. Now we have learned what is a dual problem, and let me copy this again. I want you to see something. I want you to see that. This is what I have already mentioned. It is a comparison between the primal and the dual problem. Okay. If the primal is maximization, then the dual problem is minimization, and the opposite. The coefficient in the objective function, which I called the cost vector. The coefficient in the objective function is the right hand side of the constraints, which I called the resources. This is for the rules of C transpose and B. Maybe this will be confusing. Let me take it away. Okay. Now the coefficient of the ith constraints العمود الواحد ايش بيعطينا؟ sorry. The coefficient of the ith constraint يعني عندي constraint مكون من x1 x2 x3. هذا لإيش راح يتحول؟ راح يتحول ل coefficient of the ith variable but بالconstraints كلهم. يعني عشان نفهم الثالثة نرجع مثلا لوين؟ على هذه. The coefficient of the ith constraint هذا بتكلم عنه. The coefficient of the ith constraint هذا constraint الأول شايفينه؟ الكوفيشنت تبعينه مين صاروا؟ The coefficient of the first variable. أيوه. without C. The coefficient in the first constraint هذا. تعال على الكونسترينت الأول، خذ الكوفيشنت كلهم، هذول راح يصيروا coefficient للفيرست variable لكن في الكونسترينتس كلهم. ونفس الشيء للآخرين. The coefficient of the second constraint will be the coefficient of the second variable في الconstraints كلهم and so on. اوكي أصبحوا مفهومات. The coefficient of the ith constraint is the coefficient of the ith variable, one in each constraint. تمام. جميل. Okay. Let us learn some facts about the dual problem. Actually, the dual of the dual is a dual. ايش يعني؟ طب أنا بقدر أعكس العملية، يعني أنا كان عندي برايمال. So I have a primal problem. Then I made a dual. Okay? A dual problem, this is a linear programming problem. Alright? Okay. So maybe somebody else will find this linear programming problem and he will say, I will take the dual of it. Okay? So if you take a dual of this, you will be back to the primal problem. So the dual of the dual is the primal problem. So start with a linear problem, take the dual again, you come back. Okay? And this is very important to understand it. Because we started with a linear programming problem with a maximization, then the dual is minimization. Okay? Now if we start with linear programming problem with a minimization, then the dual is a maximization. Okay? So let us see. This theorem says, given a primal problem, as in 1, the dual of its dual problem is again the primal problem. This is what I just explained. Okay, so let us start. Now, assume we have the original dual problem. Like, let me go back and say, okay, assume we start with this primal problem. Let me copy it and put it here. So assume we have this primal problem. Take the dual. So the dual is this. Okay, as we have done before. Replace these with a transpose and this and with the new variables. Okay. Now, what we do? Change it to maximize. Change minimize to maximize. You know how to do that. Multiply by negative. Right? And if we multiply this side by negative, then we change this is the variable. Okay? Good. So, now take the dual of this. We have reached, this one and this one are the same. Now take the dual. What is the dual of that? From here to here, take the dual. Okay, what we get? Maximize to minimize. Interchange the rules of these. Here we go. Okay. Now, I forgot something to mention. Let me go back. I forgot something to mention. What was it? Here. Maybe you have noticed it. Here it was less than or equal, and then here it became greater than or equal. I forgot to mention this, okay? It is mentioned in the examples above. Let me make sure that we did not miss it above there. Okay, we missed it. So we will go back and fix all this. And this will be greater than or equal. And this will be m. And above there, okay, above there they are the opposite. It is greater than or equal in the constraints above there. Below down is less than or equal, so it is fine. So بالانتقال من برايمال إلى dual أو من dual إلى برايمال لازم نعكس الأقل منه أو يساوي في constraints. Okay. So again, let's go back to the proof. Where were we? So we started with a primal problem. We made a dual, and then the dual we changed it from minimize to maximize. It is still the same, the dual. Okay, we multiplied by negative. Now take the dual, interchange B and C. Okay, and then we get that. Okay. And then this is what we have stopped at. This was less than or equal, so we made it greater than or equal because we are moving to a dual. Okay, now what's happening? Multiply negative again, we get that. And this minimization make it maximization, but multiply the function with negative, so we get this. And this is the primal problem. Good. So what we have shown here that starting with the primal problem here, take the dual, play with it, take the dual again, play with it, we get the primal problem again. So the dual of the dual is the primal problem. Okay, remember that the dual is a linear programming problem, so we can start with it. Take the dual of it, which is the primal, and take the dual again, then we get the dual. Okay. وكيف بدكم تفهمون اتكلمها بالعربي؟ عندنا linear programming problem، ايش ما تكون take the dual and then take the dual, you come back to where you were. لأن كلمة الدول مش محجوزة لحدا. أعطيني أي linear programming problem أنا بقدر آخذ الدول ليها. يعني مثلا we have here primal problem, take the dual. The dual is a linear programming problem. Maybe we come 2 days after that and take it as primal problem. It's okay, we call it primal. Then we take the dual of it, that's fine. So the idea هنا linear programming problem. Take the dual again gives you the original one. Okay. So the name dual is not preserved for any thing special. Any linear programming problem can be the dual of some other linear programming problem. Okay. Let us see what more theorems we have about the dual. So actually we have something here important for us for later. Let's take a theorem and its proof. Okay, what this theorem says? Okay, the linear programming problem in canonical form given by. Okay, see what this theorem says. If we have this primal linear programming problem in canonical form as a primal problem, take the dual. It's dual. Again, interchange this and this. Okay. But here we have equality, and here we have inequality. Here we have x to be positive. Here we have w is unrestricted. It can be positive, it can be negative. So in this theorem we are saying if we have a linear programming problem in canonical form, then it's dual. The constraints in there are inequalities and the variables are unrestricted. So this is the idea if we have it in canonical form. Okay, so let us prove that. So assume we have this problem in here, in canonical form. What we have done in here, we change this to what? To this. Ax greater than, less than or equal b. So what we have done, instead of writing this ax equals b, we wrote it in two ways. Ax is less than or equal b and ax is greater than or equal b. We can do that, right? And then we change this to be negative ax is less than or equal negative b. So now we replaced this here with this one and this one as we have now here. Okay? Okay. Now rewrite them in matrix forms. What we get? We get that, like both of these are written this way. Okay. Now take the dual problem. Actually what we have achieved from moving by playing with that is writing the equality with inequality. Okay, but we splitted the matrices as two partitions, A and minus A, B and minus B. Now we can take the dual. Remember, we can take the dual only when we learned above there, when the constraint is inequality. Here it is telling you how the dual look like when the constraints are equality. So بلغة أخرى اللي تعلمناه فوق how to find the dual was for the standard form. For the canonical form هذه الثيورم بتقول لك كيف. بس إيش بكون إضافة بالمقابل إنه W is unrestricted. So هاي هي الأيديا هنا، الانتقال من هذه إلى هذه والانتقال من هذا إلى unrestricted. Okay, so let's keep going for the proof. So we have written the canonical form with less than or equal. Now take the dual. We can take the dual as we have learned before. So the maximize will be minimize. And now interchange this and that. Interchange them. Now this is our new W. We named them U and V because it is split into two vectors. And now B minus B, take the transpose, it is B transpose minus B transpose. Okay. Now, and also take the transpose of this matrix this way. And here we go. And greater than or equal C because we have interchanged. So C will take the place of this vector here. And B take the place of C. So this is the dual problem. This is here is the dual problem. Okay? So let us play with it a little. Multiply the matrices. What we do from here to here is just multiply them. So this times that and this times this. So we get this. Take B transpose as a common factor. Okay? Again, multiply these. This by this and this by that. Remember, U and V here, they must be positive, right? Both of them positive. هذا اللي عملناه لما طلعنا الدول. يكون الفاريبلز تبعون الدول positive. Okay, then multiply these, what we get? Okay, as you see here. وهذول هيك. الآن الحركة W هنا let the W mean U ناقص V. إذا عملنا هيك بصير هذا A transpose W greater than or equal C، يعني بصير هذا W وهذه بصير B transpose W وهذا بصير W A transpose W وال W unrestricted. Why? Because U and V are positive، لكن ما بنعرف مين أكبر من ومين أصغر، which is greater and which is less. The subtraction U minus V can be negative, can be positive, can be zero, can be anything. So U minus V is unrestricted, which means W is unrestricted. Good? Okay. So again, the theorem tells us when we are in canonical form, and we want to take the dual, we must do that. With emphasizing that having equality here means having inequality here, and having this positive means having this unrestricted. Good. Now, what is next? One more theorem. Okay, now what this says. Now this says if you have a linear programming, but this time X is unrestricted, then the dual is okay, fine, change this and that, interchange them, that's fine. But it says now if we have inequality in the constraints, then we must have equality in the constraints. Inequality in the constraints of the primal leads to equality in the constraints in the dual. And also we have, if X, the variables here are unrestricted, then these are not unrestricted, they must be positive. يعني هذا تقريبا عكس الثيورم هذيك، ها؟ تقريبا عكسها، ها؟ أكيد، لأنه إذا كانت في الثيورم الأولى، حتى ما عندي رغبة إني أبرهن هذه، هنا في الصندوقين الأخضر الثانية هي الدول من الأولى، صح؟ طيب أنا لو أروح على الثانية وآخذ الدول ليها مش بيعطيني الأولى؟ طيب، لكن هنا أكبر من أو يساوي الكونسترينتس، هنا أقل من أو يساوي. أوكي. البرهان نبدأ في هذه احنا وبناخذ الدول ليها. قبل ما ناخذ الدول ليها عفوا بنغير شكلها شوي. So this maximize now is minimize، لكن ضربناه في نيجاتيف. وهذه صارت أكبر من أو يساوي مقابل ضربناها في نيجاتيف. يعني هي نفسها اللي فوق. و x is unrestricted. Now take the dual of this. The dual is المينيمايز الدول له ماكسمايز، وهذول بنبدلهم. هيهم. والمينيمايز أصبح ماكسمايز. جميل؟ والدبليو هذه أكبر من أو يساوي زيرو، وهذه مساواة. Now write the dual as، غير شكلها، شيل السالب، فالماكسمايز بتحول إلى مينيمايز. جميل؟ وشيل السالب من هنا ومن هنا، خلاص انتهينا. تمام؟ لكن السؤال هنا كيف انتقلنا من الدول هذا الدول كيف حصلناه؟ بنفس الطريقة اللي اتبعنا فيها U و V، بنفس الطريقة اللي عملناها فوق. وراح اتركها ما راح اشرحها، بدي اياكم تفكروا فيها لحالكم. طيب اذا هذه الثيورم بتحكي بانه اذا كان عندنا linear programming والفاريبلز unrestricted، فالدول بتاعينها الفاريبلز restricted positive. طيب good. الآن let us summarize what we have seen in the above problems. The theorem sorry. هذا مهم الآن نستوعب بالضبط شو اللي عملناه. اوكي كونوا معي الآن. Primal problem هنا، dual problem هنا. اوكي. The ith constraint is an inequality. عندنا ith constraint بيكون inequality. ith constraint بالدول هذا بيؤدي الى انه الفاريبل ايش ماله؟ سوري خلينا نوضحها. ith constraint بالبرايمال هو inequality. واحنا شفنا قبل شوي ith constraint في البرايمال يعني ith variable في الدول، تكلمت عنها صح؟ ith constraint في البرايمال يعني ith variable في الدول. وحتى اشير لها مليح ارجع اذكركم فيها لما كنت اقول انا في الاخضر هذا اللون اللي عملته هنا، هذا ith constraint، هذا first constraint بيعطينا coefficient of the first variable and so on. The ith constraints gives the coefficient of the ith variable. جميل؟ جميل. طيب اوكي. والان بدنا نستفيد من هذه الثيورمز اللي هنا. تذكروا هذا في المربع الاخضر هنا وايضا في المربع الاخضر هنا، وهذا الدول له اللي هو هذا. طيب اوكي what's next? So the ith constraints إذا كان less than or equal فالvariable is positive. هذه من وين بنجيبها؟ من وين؟ طبعا هذا بيفترض هنا أنا قطعته من هناك، هذا بيفترض بأنه هنا maximization وهذا minimization. اوكي. فال ith constraint less than or equal then ال positive، ith constraint less than or equal then ال ith coefficient is positive. هذه من هنا من هذه الثيورم. اوكي. هنا the ith constraint is an equality. The ith constraint is an equality. عندها ال ith variable is unrestricted. من وين هذا جبناها؟ من الثيورم اللي فوق. The ith constraint is an inequality. هذا the ith constraint is an inequality and therefore the ith constraint is an inequality. Oops, here we go. And therefore the ith variable is unrestricted, can be positive, can be negative. okay. الآن الopposite، إذا كان الjth variable is unrestricted، الjth variable is unrestricted then the jth constraint variable هنا constraint هنا constraint هنا variable هنا dual الاتجاه بالعكس بالعكس بالاتجاهين. اوكي اذا كان الفاريبل unrestricted اذا كان الفاريبل unrestricted فالconstraint equality من وين عرفناها هي؟ من هنا هذا variable unrestricted وهذه equality. جميل. طيب إذا كان الفاريبل ith variable is 0 the ith constraint is inequality. The jth variable is greater than or equal 0 the ith constraint is inequality. من وين جبناها هي؟ من هنا. من هنا هيك إلى inequality هيك هيها greater than or equal. أنا عملت عجقة هنا. أوكي هذا positive يعني هذا greater than or equal. So the ith variable is positive or 0 then the ith that's in the primal in the dual that means the ith constraint is inequality. Okay, number of variables, number of constraints both ways. You already answered me for this. Okay, طيب لاحظ هنا هذا maximization وهذا minimization. الآن البرايمال problem maximization طب كان ممكن نبدأ with primary problem تكون minimization ويكون عندها الدول maximization صح؟ فبصير تبديل لهذه الأدوار. يعني افهم علي شو بدي أقول الآن because you will need it the next example and you will need it to answer questions. Okay. Remember that theorem 3.1 tells us to read the table from right to left and from left to right. That is, if the heading of the primal and the dual are interchanged, the resulting table remains valid. تمام؟ يعني تقدر تقرأ إذا كان عندك primal maximization لminimization أو العكس. ممكن يكون عندك minimization للبروبلم بصير الدول بروبلم هنا مكان الدول بروبلم هنا ممكن تعتبره انه مكان البرايمال بروبلم والبرايمال هي الدول. يعني بتقدر you can read the table from left to right او right to left. تمام؟ لكن بدك تكون حذر هنا. بدك تنتبه على شيء زيادة. ايش معنى هذا الكلام اللي انا بقوله؟ انتبه. Note that the table shows how to find the dual of maximization problem with greater than or equal. لاحظ الماكسمايزيشن كان عندي greater than the constraint is in equality or equality less than or equal or equality. So it is inequality of type less than or equal or it is equality. هذا مربوط مع المينيمايزيشن مع maximization So إذا كان عندك problem الدول عندك maximization وبدك تحول لدول بدك تتأكد إنهم هذول الاثنين موجودين عندك. يعني ما بدك you are not allowed to make a dual when you have a maximization and greater than or equal. You need no less than or equal. طيب وأيضا if you have minimization بدك العكس. إذا كان problem the original problem is minimization and you want to take the dual then you must have either equality of type greater than or equal or equality. Then you take the dual. Somebody may ask, oh okay, what if I have a minimization problem but with less than or equal? What I do? Because here it says if you want to take the dual of a minimization problem you must have the constraints to be either equality or greater than or equal. One of you may ask, what if I have a minimization with constraints less than or equal? How I do take the dual? Then the answer is convert the less than or equal to greater than or equal by multiplying negative on both sides. Okay? Same question will be, what if I want to take the dual of a maximization, but instead of less than or equal, I have a greater than or equal, then I will say multiply by negative again and make it less than or equal, and then take the dual. So this very graph explains what I am saying. And to make this clear, we must work these examples. Now we go here, copy and paste. Now I will let you think about finding the dual problems of these. Notice that the primary problems here are not ready to find the dual problem right away. You need to play with it. So have a look at it and tell me, how do we reach that dual problem? So we have maximization. We have maximize. And we said in the maximize, we must have less than or equal, right? Let me see. Let me go back. The maximize needs less than or equal. Oh, we have less than or equal, that's good. Here. The maximization requires you to have less than or equal or equality. Do we have it here? Yes, this is a maximization and all constraints are of kind less than or equal. Okay, thank you, very good. So we can go right away and find the dual. So to find the dual, this is the primal, and to find the dual, we will make maximize, minimize, and we will take this vector here with these and interchange them, right? So we will have this here coming here and here and here, and 3, 2, 1. Let me give them color to emphasize how we do this. So the cost vector here is the constraints, the resources, and the resources vector here is now the cost vector here, and that matrix now is the transpose. Now if you notice, we used to say that the coefficient of the first constraints are the coefficient of the first variable. You like this coloring? Again, the coefficient of the second constraints are the coefficient is the second variable of the second variable. Again, the coefficient of the third constraints are the coefficient of the third variable. Good. Now what about the following? Notice here x1 is restricted, positive, so w1 is restricted. You agree with that? Now pay attention to what's happening. Why this is happened? Because the first constraint, I want you to learn something now. Now these examples will help us to put all things together. كل شيء تعلمناه في هذا السكشن حطيناه في هذا المثال. فانتبه عليه. The first constraint tells you what is happening with the first variable. Again, first constraint in the primal tells you what shall be happening with the first variable in the dual. First constraint here is less than or equal. Okay? So first variable is positive or 0. Huh? How do we know that? Let's continue. Now look at the second constraint is equality. Okay? Equality. So what's about the second constraint, second variable here is unrestricted. Where we learned that in the theorem. Do we have this summarized in the table? Yes, it is summarized in the table. It says the ith constraint inequality means that the ith variable is unrestricted. Here it says that the ith constraint is inequality, then the ith variable is greater than or equal 0. Good? Good. Now, in the second example, we will use this. If we have some variable which is unrestricted, then the jth variable is unrestricted, then the jth constraint, when we talk about variable in the primal, then we talk about constraint in the dual. When we talk about constraint in the primal, we talk about a variable in the dual. So if a variable, the jth variable in the primal is unrestricted, then the jth constraint is equality in the dual. And if the jth variable is greater than or equal 0, then the jth constraint is inequality. And we go opposite way. We go opposite also. And you can do this, because theorem 3.1 says the dual of the dual is the original problem. This is very important. You need to understand it. We are putting everything in the section here in these two examples. And the number of variables, number of constraints. كويس. الآن فكر لما أنت تتكلم عن constraint في البرايمال، هذا بيعطيك صفات الفاريبل في الدول. وتتكلم عن variable في البرايمال، هذا بيعطيك صفات الكونسترينت في الدول، والعكس. variable هنا constraint هنا، constraint هنا variable هنا. Okay. Now okay, good. So now let us go to the third inequality. The third inequality here is inequality. It is not equality. Okay. So, but you see what's happening here. X3 is unrestricted. Okay, X3 is unrestricted. And the third equality, okay. Let us go and find when we have a variable is unrestricted, what happens. Please pay attention to this. When we have a variable in the maximization unrestricted, which is we have the third variable unrestricted, okay? So the third constraint shall be equality. So when I go here, I say, so let me give it another color. Okay. So the third variable is unrestricted. That will cause the third constraint to be equality. Okay? Now, what caused the second constraint to be unrestricted is this color, the same thing here we talked about. Okay? Now, W3 is positive, huh? Let's go, how did we learn that W3 is positive? Because of this. It says here what? The ith constraint is an equality, so the ith variable is positive. يعني if third constraint was inequality. هيو. The third constraint was inequality. لذلك هذا اللون هو بده يكون سبب انه هذا positive. هذا السبب انه هذا positive. وايضا الاولى الازرق constraint كان inequality، فهذا السبب انه هذا positive. فأنا بدي أرجع أشيل هذا أصلا من هنا. تمام؟ أوكي جميل. الآن نرجع لورا. لما يكون الفاريبل positive، الفاريبل positive inequality ايش بتكون؟ الكونسترينت المناظر بيكون inequality. فالسبب، بدي ألوان كمان، فالسبب في هذا هنا مين هذا؟ جميل. وألوان أخرى. السبب في هذا هنا مين؟ هذا. بوم. كويس؟ جميل جدا. إذا كل inequality أو equality أعطتني شيء بخصوص الفاريبلز. لاحظ الانكواليتيز فوق أعطوني معلومات عن الفاريبلز، والvariables above there primal gives me information about the constraints. When a variable in the constraint is when a variable in the primal is greater than or equal 0, the ith variable, then the ith constraint is inequality is greater than or equal. Okay? When the variable is unrestricted, then the constraint is equality. When the constraint in the primal is inequality, less than or equal, then the variable is bigger than or equal 0. When the constraint is equality, the variable is unrestricted. Be very careful. When I talked about x1 is greater than or equal 0, then I said the first variable is greater than or equal 0, then I said the first constraint is equality, I mean greater than or equal 0. Okay? But when I go the opposite, إذا كان الفاريبل تحت عندي primal greater than or equal 0، الconstraint بيكون less than or equal. ها؟ هذه اللي نتكلم عنها. إذا كان الفاريبل هنا موجب، فالconstraint هنا هي less than or equal. Okay? Let me clean it. تكون less than or equal. So pay attention to this. لكن هنا لما يكون greater than or equal 0، شو بتكون هذه؟ greater than or equal. مرة أخرى، لأنه هذا الشيء تكلمنا عنه هنا. لما تكون أنت عندك maximization عندك less than or equal، minimization greater than or equal. هذا لازم تشوفه هيك. طيب، فتأمل هذا المثال ورتب المعلومات في ذهنك. خلينا نروح على مثال آخر، وهذا المرة خلينا نجيبه على يسار الجدول أو على يمين إذا عندنا فراغ. Okay. This is the very last thing in our lecture for today. Okay, good. Now, we have a minimization. Okay. We have a minimization now. Here we have minimization. This is the primal problem. So the dual problem will be maximization. So we will move from the right to left. Okay. الآن pay attention. The first inequality, the first is constraint is inequality. Good? So that means Can I have this in the minimization? I must have greater than or equal. This is less than or equal. So what I do? I must convert this, right? So I must convert this to x1 minus x1 minus 2x2 minus x3 to be less than, to be greater than or equal minus 7. So I want to replace that. Okay, so I will not consider the less than or equal here because I just changed this constraint. Okay, now I go and look the first. So if I do this now again, before I keep going, I need to okay, now I have here minus 7, 5 and 3. They are here. See, minus 7, not 7, 5 and 3. Now I have here 2, negative 3, 1. So 2, negative 3. Where did we go? Oh, so I have 0 because I have, let me emphasize it here, plus 0 times x3, right? x3 does not appear because it has 0 coefficient. So 0 and negative 1. Okay. So I have how many constraints? I have 4 constraints in the primal. So I will have, 3 constraints in the primal. So I will have 3 variables in the dual. Okay. I have 4 variables in the primal, so I will have 4 constraints in the dual. Variable and constraint, they interchange. Okay, good. Now, the first inequality is greater than or equal. So it is this one here. So that will cause what? The first variable to be positive. Great. So blue goes with blue. Good. Now let us see. The second constraint is equality. The second constraint is equality. That gives the second variable must be unrestricted. The second variable must be unrestricted. So this will give that. Good? Okay, now we have the third constraint is greater than or equal, as it is here. So the third variable is positive. So here, the third variable must be positive. Okay, good. Now we have transferred informations from constraints to variable. Constraints in the primal to variable in the dual. Now we keep going, we'll convert information on variable on the primal to constraints in the dual. Okay, let's see. Variable in the primal. The first variable is positive. So we go here. The variable is positive. That means the first variable is positive. That means the first constraint shall be less than or equal. So what caused this is that. Good. Now, again, the second variable is greater than or equal 0. So the second constraint will be less than or equality, less than or equal. The equality is less than or equal. Okay. Same thing for third variable. Oh, okay, all of them give the same. And also again Same thing for the fourth variable. Okay, so we're done. So go again and review these two examples and go work at least two exercises on this, because in these two examples we have summarized everything we have learned in this section. This brings us to the end of today's lecture, and if anyone of you has any question, please go ahead.